My name is Izzy Stoll, and today I'll be talking about modeling biologically relevant performance on an audio discrimination task, moving really from convolutional neural networks to spiking neural networks. The objective here is to build a neural network implementation of the auditory system, then train this neural network on multiple species to classify bird calls. The motivation here is that biological data is noisy, and like other neuroscientists, I'm interested in how we process these noisy signals. Also, our cortical neurons are noisy. And again, like other neuroscientists, I'm interested in how we use noise to enhance the computation. And really, Nengo is an excellent toolkit to address these questions. Nengo is a Python package for building, testing, and deploying neural networks. It's built on the neural engineering framework and utilizes vector symbolic algebras and semantic pointer architecture. It is great for building biologically plausible spiking neural networks. So first, we can go over the state of the art, how audio data is processed currently. So we see here audio files from 5 different species with 5 different characteristic bird calls, and we've mapped out the amplitude of these bird calls over time. How we normally process these data is that we complete a fast Fourier transform, convert these data to MEL frequencies, perform a discrete cosine transform, plot the MEL frequency cepstral coefficients, adjust the window, eliminate the noise, and then use these images to do the audio analysis. So it really just becomes an image processing task. So then we run the images through a convolutional neural network, which then spits out a prediction of the bird species from that bird call. So it's really important to note that this is not how birds do it. This is not how we do it. We do not take a 5-second audio clip and convert it to an image and then do frequency analysis on the patterns of that image, right? So we're actually processing the data in real time. We are completing Fourier transforms in real time and processing the audio data as audio data. So how do we do this? In birds and in mammals and ourselves, our ears perform a Fourier transform. So sound enters the cochlea through the oval window, and high-frequency noises activate hair cells near the oval window. Lower frequency sounds travel through the entire cochlea and activate hair cells at the apex of the basilar membrane. And so it's important to note that hair cells are mechanoreceptors. So when these hair cells are deflected, they force open an ion channel and ions flood into the cell. Those ions are a flow of current, and so the cell changes its voltage. That neuron, the hair cells are sensory neurons, that neuron sends a voltage signal into the brain. And so the auditory cortex within the brain actually has a tonotopic map. So some neurons are sensitive to low frequency signals like 250 hertz, while some neurons are sensitive to higher frequency signals like 4,000 to 20,000 hertz. And so we have this tonotopic map across auditory cortex. So what happens when we place a recording electrode in auditory cortex? Well, we see these spike trains, right? So here we have a picture of, a tutor bird, an adult bird who knows the song really well, is singing, and those frequencies are mapped over time. And so we can see this, the characteristic frequency spectrum of this song. And a little baby bird then has neurons that are active in response to each of these frequencies. So these neurons are frequency tuned. And so we see the distribution of neurons and the spike trains that are active across the bird song. And so this little baby bird has to learn to recognize conspecifics, heterospecifics, and it has to be able to figure out what are different individual birds within the same species, and what's the song of a bird of a different species which may have less relevance to its life. So this is a really hard classification problem. And I just want to show here, this is some fMRI data from human subjects, 3 different individuals. And all I really want to note here is that when the data is really noisy, we're better able to distinguish frequencies across the frequency spectrum. And this is something that's really characteristic of cortical neural activity. It's not true in spinal neurons, right? So our spinal reflex circuits are so robust to noise. If there's a stimulus, the neuron's firing. If there's no stimulus, the neuron is not firing. That is not true in cortex. Our cortical neural networks are incredibly noisy, and it appears that this noise allows us to better distinguish signals. And so that's kind of something that we're going to get at when we talk about how biological spiking neural networks are actually processing noisy ambient sound by being noisy themselves. And so really what we're trying to do here is extract a signal from the noise, right? So these populations of neurons are active. So we want to say, okay, this neuronal ensemble is active and it's representing the frequency spectrum of the bird call that's happening. So we can use a randomly connected neural network with a random projections model, right? And this gives us like a uniform random distribution. And really what we want to know is what's the uniqueness of that neuronal ensemble? What's the complexity? What's the information that's being encoded by these active and non-active neurons? So now we're getting to this NENGO project, how we process data like a biological system. And so we've created a model neural network that is BIRD approved, that's a lot more like the biological system. And so what we'll see here is the stimulus, the audio file, and then we'll see layer 1, the Legendre delay network, and layer 2, another Legendre delay network that's going to act as a mixing ensemble. So these are two populations of neurons that are responding to the stimulus. So we've built a model of auditory cortex. And so what we can do is follow the audio file through the stimulus and look at the layer 1 of the Legendre delay network and layer 2 of the model of auditory cortex, which is also a Legendre delay network. And what we're looking at is the neurons that are tuned to each frequency over time. And so when there's not much signal going on, there's just ambient nature noises in the background, we see something really close to a uniform random distribution in layer 1. But when there's a bird call, these neurons are very active in a very ordered way. They're encoding each frequency with these spike trains. And so this looks a lot more like the biological system. It looks a lot more like avian auditory cortex. And it's important to note that the Legendre delay network is performing a pseudo Fourier transform. And so this is allowing us to predict with some level of certainty, with very high uncertainty, which bird species is making that call. So to do better, we can measure the complexity of the signal. And so again, when there's no bird call happening, when there's just ambient noise in the environment, we have something close to a random uniform distribution. But when there's a bird call, we see this very ordered spiking activity across the frequency tuned neural population. And this is, again, we're trying to extract a signal from the noise. And so when we map out the complexity, essentially we're taking the entropy of this Legendre delay network and we're comparing it against the entropy of the random uniform distribution. So really we're trying to identify the information that's being encoded in that layer 1 or layer 2. And so we can do a cross-entropy loss function and do a little bit better on this prediction. So we can compare the firing patterns between data sets. So with one stimulus, a particular bird call, we get a characteristic response in the mixing ensemble. With a very different stimulus, a very different bird call, we get a different characteristic response across the mixing ensemble. And so again, we're doing a cross-entropy loss function comparing, again, the entropy of layer 1 or layer 2 against the entropy of the random projections model, the uniform random distribution. And what we can do is start to identify the probability of each neuron firing due to its tuning. And so we get this characteristic pattern of neurons firing with their frequency tuning or their higher order feature extraction in response to each bird call. And so we're decoding the neural populations to classify these samples, doing a Fourier transform in real time. And so we can see as the bird call is, the recorded bird call is happening, we see the probability of firing in these neuronal ensembles, and that allows us to decode with some level of accuracy and some level of certainty which bird is singing. And so we can systematically evaluate these spiky neural networks using the Heidelberg standards. So that's not something we've done yet, but it's really important to note that spiky neural networks typically do not perform well against convolutional neural networks. There is a reason that everybody uses the convolutional neural networks. They perform a lot better at this stage. However, there are some advantages of our new method. First of all, it's biologically plausible. We know convolutional neural networks can have hundreds of layers. No one knows what they're doing. Spiky neural networks typically have only 1, 2, or 3 layers. This is far more biologically plausible to have a Legendre delay network for layer 1, another Legendre delay network to create the mixing ensemble for layer 2. We have a complexity ensemble extracting those features in layer 3 with a random projections ensemble, a memory ensemble, an error ensemble, and a prediction ensemble. These 7 layers are far more biologically plausible. This is also a small network. We really only need 100 neurons per layer for a total of 700 neurons. In addition, we're completing real-time analysis, which is not dependent on heavily pre-processed images to train and run the classifier. So the next steps here are really to model the complexity node with a semantic pointer ensemble. We can evaluate the performance of the neural network on large data sets, including BirdClef 2024 and BirdClef 2025. We can also use the speech standards created by the Heidelberg team. We can also compare performance on digital hardware versus analog hardware by running this not only on a CPU, but also on a spinnaker and a brain drop. So we can really identify whether endogenous noise in analog hardware affects the accuracy, compute time, and energy requirements of this classifier task. So I just want to say thank you so much to the team here at Waterloo University, Chris Eliasmith, Terry Stewart, Michael Furlong, and the whole rest of the team. Thank you so much. It's been wonderful to visit Waterloo University and work with you, and I encourage everybody to use the Nego toolkit.